Okay, so for our second video here, we're going to be looking at some electrochemical cells and talk about exactly what that is. So an electrochemical cell, typically known here as a voltaic or galvanic cell, basically what this is a system that uses a spontaneous redox reaction to drive electrons through an external pathway so that work can be done with those electrons. And it typically consists of three components. Well, actually four. There's an external wire involved that I haven't listed here, but three main components. So a cathode, right? This is the positive electrode, or the electrode at which the reduction occurs, right? Because electrons are moving to it because it's the positive electrode, so they're going there, reduction is going to occur. The anode, this is the negative electrode. This is the one where the electrons come from, right? And so it's losing electrons, which means it's the electrode at which oxidation is going to occur. And then you've got something called a salt bridge, and basically what this does is it allows ions to move within the cell so that you can maintain electrical neutrality at the cathode and anode. Because if you have a buildup of ions in one of your cells, right, it's going to quench your battery. The electrons are not going to want to move, and your flow of electrons is going to stop, and so you'll not get any more work out of it. So I'll show two diagrams, and I understand that the descriptions here are maybe a little blurry. So these two things here are the electrodes, and this one is a zinc electrode. This one is a copper electrode. All right, so here's your salt bridge, right? It says electrons are flowing this way, right, from the zinc to the copper. In this, you have zinc sulfate. Over here, you have copper sulfate. All right, so basically what that means is that we have zinc ions and we have sulfate ions. And over here, we have copper ions and we have sulfate ions. And so you have your cathode over here, right? That is the plus. And you have your anode over here, which is the negative, right? And what happens is as electrons move, right, zinc is oxidized, which means its charge increases. So it goes from zinc to zinc plus. Those zinc ions come into solution. And over here, right, what happens is you have copper, or on the cathode side, right? I shouldn't say over here because you can't see where I'm looking. On the copper side, you have copper ions going to copper, right? And they are coming out of solution and plating onto the electrode. And so eventually you're going to have an imbalance of charge, which is where the salt bridge comes in. You might be able to see that it says sulfate ions are moving that way, right? Because this cathode is generating positive ions. And it says zinc ions, right, are moving that way because you're going to have an overload of sulfate ions over on the cathode side. Right, so the salt bridge is basically just allowing your ions to move from side to side. The next picture I'm going to show is the exact same setup. It just doesn't have a specific salt bridge, right? It has a porous disc, right, or a semi-permeable membrane that separates the two sides so that ions can flow. In fact, in this one, it only says anion flow, right? So anions are moving from the copper side to the zinc side because those are the negative ions. They are moving over to the anode side to quench the extra positive charge that's going on over there. But it is exactly the same thing going on. You have ions moving through your porous membrane. You have your zinc anode, your copper cathode, and your electrons moving from anode to cathode. So when we talk about galvanic cells and cell potential, right, we need to talk about, well, cell potential, right? Because when we're talking about voltaic cells, there is electricity moving or energy moving, and so we call that some cell potential, right? This is designating a number to the work that we can get out of it. So cell potential, or E cell, is the potential difference between the two electrodes. It's often looked at under standard conditions, right? So if you remember from our talk about standard entropy and standard Gibbs free energy, all right, that little circle denotes standard conditions. So that's 1 molar, right, and 1 atmosphere. And so this potential difference is what drives electrons through the cell, and the cell potential difference, right, the E cell, is also referred to as electromotive force, or EMF. And cell potential, and or EMF, is measured in volts, and 1 volt is 1 joule per coulomb, right? And if you remember, coulombs have to do with the fundamental charges. We'll talk about coulombs later. At this point, it's not as important as just knowing that the cell potential is measured in volts, and that volts are equal to 1 joule per coulomb. So standard reduction potential. Okay, standard reduction potential, right? The red stands for reduction, and this circle is telling you standard. It is a measure of how much a species wants to gain electrons, or its potential for being reduced. All right, standard reduction potential. And it's just a measure of how much it wants to take electrons, and it as well is measured in volts. And this equation here should look very familiar to you, as we have used this equation about 7 times so far for various things. Basically, the cell potential is the difference between the potentials, the reduction potentials at the cathode, and the reduction potentials at the anode. And no discussion of standard reduction potential would be complete without a discussion of She, or the standard hydrogen electrode. And this is a defined electrode with the reaction of this, right, where you have hydrogen ions taking in electrons being reduced to form hydrogen. And we have defined this particular reaction as having a reduction potential, or a standard reduction potential, of 0 volts. So in essence, this means that all of the other reduction values on a standard reduction potential chart are defined relative to their difference from this electrode. Right? It doesn't really change anything about their values, but it's good to know that all of the values that are on there are defined relative to the standard hydrogen electrode. Okay, so let's walk through a calculation looking at this. So we have this particular equation, right? And one thing you'll notice, we can, if we know we're working with zinc and copper, right, we can look at the reduction of both of these, right? So the reduction, 2 electrons, right? The reduction equations of both of these will look like this. However, in this case, only one of them is being reduced, right? So we're going to have to figure out which one is our cathode and which one is our anode. So remember that the cathode is where reduction takes place. And if you look, we have copper plus 2 on this side, copper on that side. So in this particular scenario, right, copper is being reduced. here in this equation, we have zinc and then zinc plus 2. Its charge has gone up. It's being oxidized. It is the anode reaction. So we place those accordingly, right? Copper being reduced at the cathode, zinc being oxidized at the anode, and then we find a standard reduction potential chart. We look up the values, we put them in, and we calculate. It's as easy as that. So one thing to note, right, if you are only given the reduction equations, right, so if you are said kind of like calculate the cell potential given the following reduction equations, right, so you would have like this and this. How can you tell which one is the cathode and which is the anode? Which is a great question. So if you are given a situation like this where you're only given the reduction equations for the galvanic cell, then you can look at the standard reduction potential chart. And when you see that zinc has a standard reduction potential of negative 0.76 and copper has a standard reduction potential of 0.34, right? The one with the more positive reduction potential will be the cathode, right? Because it is more likely to be reduced. So the more positive the standard reduction potential, the more likely it is to be reduced. The higher the value between the two, that is going to be your cathode, right? Because it has more potential to be reduced, and reduction happens at the cathode. So if you ever encounter a situation like that where you're only given the reduction equations, that is how you figure out which one is the cathode and which is the anode. Okay, good things to remember. Standard reduction potential tables are listed in order of decreasing tendency to be reduced, so the species with the most positive standard reduction potential are the most likely to be reduced. And the opposite of this is true for species with a negative standard reduction potential, right? The species with the most negative standard reduction potentials are easily oxidized when the reaction is run in reverse, right? So like take our zinc, for instance, right? This has a standard reduction potential, we said, of negative 0.76 volts. So the opposite, right, would be positive 0.76 volts, which means it is likely to be oxidized, right? It is more favorable to be oxidized, going from neutral to +2. The charge is increasing, oxidation. So when you run that reaction in reverse, it is likely to be oxidized because it has a more favorable value in voltage. Okay, so that's it for this one. I will see you in the next video.